Good evening, everyone. I hope my screen is visible to everyone and I am audible. So we will start at 6:02 or 6:03 as usual. Hope more people will join by then. So today we will discuss some questions related with communication theory and one question related with probability. And in all of the questions that we are dealing today, they are somehow related with probability theory. Okay, but some of the questions are from communication area. So okay, we will wait for a few minutes and we will start. Okay, let's start. So I hope you can see the first question. It is as follows. A binary symmetric channel or a BSC has a transition probability of 1 by 8. If the binary transmit symbol x is such that probability of x equal to 0 is equal to 9 by 10, then the probability of error for an optimal receiver will be. Okay, so the question is fairly straightforward, two-line question. But in order to solve this question, you need to have some preliminaries. Okay, so before discussing about the question, let us first see what a communication channel is. Okay, uh, so a channel, uh, so a communication channel will have an input and output, which are random variables. Okay, let us assume that the channel is a finite input channel. That means the input can be one out of some finite number of elements. Okay, let us assume that this input can be from this set x1, x2 up to x, say capital M, and the output y can be anything. And the channel is usually modeled using conditional probabilities. Okay, so suppose I'm transmitting one out of these m, I will call it as symbols. Okay, m symbols are there, x1, x2 up to x capital M. Okay, say I'm sending one symbol, say xi, I am transmitting. Then at the output, the receiver will receive some y, okay, some small y, which is a realization of the random variable capital Y. So a channel is characterized with this conditional probability. Okay, so here we can say there are m such probability distributions. The first one is probability of y given x equal to x1, probability of y equal to y given x equal to x2 up to probability of y given x equal to xm. Basically, these probabilities are called transition probabilities. These transition probabilities together characterize a communication channel. Okay, so what is the physical meaning of these probabilities? Let us focus on this first probability. What is it? Probability of y given x1. What does that mean? It means that I'm transmitting symbol x1. Then what is the distribution of the output? Okay, with which probability I will receive some small y. So this probability capital Y equal to small y given x equal to x1 denotes the probability of receiving this small y given the fact that x1 is transmitted. Okay, so there are m such probability distributions. These together characterize a channel. Okay, now let us focus on the question and a binary symmetric channel. So a binary symmetric channel is a two input, two output channel. You might have seen this diagram many times during your BTech studies. Okay, so this is a binary symmetric channel. It has two inputs. The input x can be either 0 or 1. And the output y is also finite. It can also take two values, either 0 or 1. Okay, so x can be 1 out of these two, and y can be 1 out of these two. So suppose I am transmitting 0, then the output of the channel will be 1 with, sorry, 0. Let us focus on 0 first. 0 with probability. What is the probability? Probability of y equal to 0 given x equal to 0. Correct? So if I am transmitting 0, then output will be 0 with this probability. Probability of y equal to 0 given x equal to 0. Similarly, if I am transmitting 0, the output will be 1 with this probability. This probability is corresponding to this branch. Okay, probability of y equal to 1, that means output equal to 1 given the input is 0. Okay, now there are two more possibilities, right, that are corresponding to the input 1. That means suppose I am transmitting 1 from the channel input or the transmitter, then the output will be 0 with probability. So this I will write here. Okay, probability of y equal to 0 given x equal to 1. And finally, if I transmit 1, the output can be 1 with probability of y equal to 1 given x equal to 1. So first of all, how is the receiver receiving 0 if I transmit 1? That can be because of various reasons. For example, a channel error can happen, right? A channel is, if it is through a physical medium, some error can happen due to the noise addition, correct? So this transition from 0 to 1 or 1 to 0 is called as an error or a bit flip. Okay, a bit means it can be either 0 or 1. A bit flip means the 0 is mapped to either 1 or 1 is mapped to 0. Okay, that is called a bit flip. In binary symmetric channel, there is something in between, right? This S. So you understood what is binary means. It is input is binary, output is binary. It can be either 0 or 1. Then what is symmetry? Symmetry comes here. Probability of y equal to 0 given x equal to 1. That means this transition probability. If the input is 1, the output is 0. That probability equal to probability of y equal to 1 given x equal to 0. That means this probability, that bit flipping probabilities are equal. Okay, so that probability is known as the transition probability, or sometimes it is called bit flipping probability. Okay, so usually it is denoted with, you might have seen with small p or sometimes with epsilon. So there will be different notations used in the literature, in textbooks. Okay, so now a binary, my statement is like this: a binary symmetric channel, these transition probabilities can be characterized just using this transition probabilities. You agree with that? So what I'm saying is that if I give this bit flipping probability, say it is p, I can find this probability and this probability. Do you agree with that? If it is p, this bit flipping probability, what is this probability? Probability of y equal to 0 given x equal to 0. Can somebody tell that? Okay, so that means if the input is 0, if the channel input is 0, then the channel output will be 1 with probability p. Then if the channel input is 0, then the channel output will be 0 with probability 1 minus p, right? That means if I am transmitting 0, then the output can be either 0 or 1. If the output is 1 with probability p, then the output will be 0 with probability 1 minus p, right? Similarly, if I am transmitting 1, then the output will be 0 with probability p. Then the output will be 1 with probability 1 minus p. Correct? So this is a binary symmetric channel model. So I will erase this. So here there will be 1 minus p, then transition probability p, and again 1 minus p. Okay, now again come back to the question. So here a binary symmetric channel BSC has a transition probability 1 by 8. Here small p equal to 1 by 8. If the binary transmit symbol x, that means the input, is such that probability of x equal to 0 is 9 by 10, then what is the probability of error for an optimum receiver? Okay, so now the question is like this. Now this p equal to 1 by 8. So what are these probabilities? 7 by 8 and 7 by 8. Correct? And the input can be either 0 or 1, and the output can also be either 0 or 1. So probability of x equal to 0. Probability of x equal to 0 is given as 9 by 10. Okay. Then what is this probability? Probability of x equal to 1. Can somebody tell that? Anyone? So the input will be 0 with probability 9 by 10. Then what is the probability of the input being 1?
1 minus 9 by 10.
1 minus 9 by 10. That is equal to 1 by 10. Correct? So now we have all these probabilities. Now the question is, what is the probability of error for the channel if I am using an optimum receiver? Optimum receiver means the best receiver. So what is the best receiver? In a communication setting, the best receiver is the following receiver. Map receiver. Okay. Map receiver. What is map? MAP stands for maximum a posteriori probability. Maximum a posteriori probability receiver. Okay, this is MAP. So this is the best receiver. So this receiver does the following thing. So consider a general channel, not the binary symmetric channel. You can consider this channel. Okay, so the output being Y, and the input can be one out of these M possibilities. So now you have to think in the perspective, in the receiver's point of view. Okay, so what the transmitter is transmitting some symbol out of the M possibilities, x1, x2, up to x capital M. Receiver is receiving some Y, but the receiver doesn't know which is the transmitted symbol. From the received Y, the receiver has to make an estimate, or it has to decide which is the transmitted symbol, right? That is a communication scenario. So here the receiver has to use the following, or the receiver does the following thing to find or decide which is the transmitted symbol. That is the MAP rule. Okay, maximum a posteriori probability rule. This rule will be used by the receiver. So it does the following thing. So the receiver can calculate these M probabilities. Okay, x2. X2 means capital X equal to x2 up to probability of xm given y equal to y. So the receiver has to calculate these M probabilities. Okay, so this is very straightforward. The receiver has y. So under that condition, conditioned on the fact that the received value is small y, under that condition, these are the probabilities, right, for each of the input possibilities. Correct? So it takes the maximum, the say it picks up, the receiver picks the maximum out of this probability, and it decides in favor of that particular symbol. Say out of this probabilities. Say this is the maximum. Then the receiver tells that, or it decides that x2 is the transmitted symbol. Okay, this is the map rule, or in other words, you can write x hat. X hat is the estimate or the decision by the receiver. X hat equal to argmax some small m. Okay, probability of x equal to xm given y equal to y. So basically, it decides, or it decides that the m that maximizes this probability. Okay, that is the map rule. Is it clear? So now I will explain this in terms of binary symmetric channel, then it will be more clear. So in binary symmetric channel, okay, so this y can be either 0 or 1, right? Because the output can only be 0 or 1, correct? So suppose I am receiving, not I am receiving, the receiver is receiving y equal to 0. Okay, then the receiver will compute these two probabilities. These two probabilities, okay? Whichever is higher, say this one is higher, then it tells that x hat or the decision equal to 0. That means x equal to 0. Suppose it's in the other way. Suppose this is like this. This probability, sorry, here there is a mistake. This is y equal to 0, okay? So it compares these two probability. So here you can see that x hat equal to 1. So did you get what I'm saying? So the receiver receives y equal to 0. Okay, receiver receives 0. Then it has to make a decision on the transmitted symbol. It can be either 0 or 1, correct? If I transmit 0 with probability 1 minus p, the output will be 0. If I transmit 1, then also the output can be 0 with some probability p, correct? So if I receive 0, it can be either 0 or 1. So it has to make a decision. That decision is made by comparing these two probabilities. Similarly, if y equal to 1, then again, this is the comparison. Given y equal to 1, correct? So here again x hat equal to 0, here x hat equal to 1. Is it clear? I hope it is clear to everyone. So now, yeah, okay. So in general, not in general, in this case, we can come back to the problem. Okay. So here I have two cases, right? So now it is asked to find out the probability of error. How can we find the probability of error? When does when does an error happen? So I will say an error happen when x not equal to x hat. What does that mean? That means x is the actual transmitted symbol. It can be either 0 or 1. And based on the received value, the receiver will make a decision on the transmitted symbol, right? The receiver doesn't know the actual transmitted symbol, but based on the received symbol, it makes a decision, correct? That is denoted as x hat. So when will I tell an error happen? An error is happened. So an error is an event where the transmitted symbol is not the, or the estimated one. X hat is different from the actual transmitted symbol, correct? The receiver makes a decision error. So now this can happen in two different ways. This can happen, the first way is I am transmitting x equal to 0 and I am deciding x hat equal to 1. And the next one is probability of x equal to 1 comma x hat equal to 0. These are the two possibilities, right, in binary symmetric channel, correct? Now I will now let us calculate this probability. Okay, so let us assume that y equal to 0, that the received symbol is 0. Then this is what the receiver does, correct? So it compares these two probabilities, x equal to 0 given y equal to 0, and probability of x equal to 1 given y equal to 0. These are the two probabilities being compared. So now we need to find this probability and this probability. So we know the channel, that means the ulta of this probability, not ulta, it's in the other way. Y given x we know, but we do not know x given y, but we need to find x given y. How do we find that? For that we can use uh, the the conditional probability definition. Probability of x equal to 0 given y equal to 0 can be written as x equal to 0 comma y equal to 0, or the intersection or the joint probability divided by probability of y equal to 0, correct? And it can be written as probability of x equal to y equal to 0. Again, I am using the definition of conditional probability into probability of x equal to 0 given probability of y equal to 0, correct? We can do this, right? So now similarly we can write this probability as well. Probability of x equal to 1 given y equal to 0 equal to probability of y equal to 0 given x equal to 1 into probability of x equal to 1 whole divided by probability of y equal to 0. Now we need to compare these two probabilities. Probability of y equal to 0 given x equal to 0 into probability of x equal to 0 whole divided by probability of y equal to 0 less than or greater than probability of y equal to 0 given x equal to 1 into probability of x equal to 1 whole divided by probability of y equal to 0, correct? So this is equivalent to comparing, because there is a common factor that we can just neglect or we can cancel out, because that is a common factor in both the sides. So the comparison will not get affected by that. So now this is just the comparison of these two. Do you agree with this? So we have all these probabilities as well. This is nothing but 1 minus p, and this is nothing but something given in the problem, and this is again p, the transition probability, that means input being 1 given that fact, the probability of output being 0, that is p, the transition probability. This is again given in the question, correct? Similarly, if the now we have assumed that the input is 0, correct? Now assume that the not input, output is 0. Now assume that output is 1. Then again we will get similar expressions. Before that, let us compute this, okay? So here, what is the value of 1 p? P is given as, sorry, where is that? Yeah, p is given as 1 by 8, and probability of x equal to 0 is 9 by 10. Okay, so this is nothing but 1 minus 1 by 8 is 7 by 8 into 9 by 10 less than or greater than 1 by 8 into 1 by 10, right? Clearly this is bigger. So whenever the output y equal to 0, then the receiver will make a decision that x hat is also equal to 0. This is corresponding to 0, right? Here x hat is 0, x hat is 0, and this is x hat equal to 1. Since this is greater, the receiver will make a decision x hat equal to 0. So irrespective of the actual transmitted symbol that receiver doesn't know, irrespective of that, whenever the receiver gets y equal to 0, it makes a decision that the transmitted symbol x hat is 0. Okay, now similarly consider this case, y equal to 1. This is first case. Okay, y equal to 1. Let us consider this case. This again I can write just like this. I will directly write like this: probability of y equal to 1 given x equal to 0 into probability of x equal to 0. probability of y equal to 1 given x equal to 1 into probability of x equal to 1. So I am directly writing this. If you want to know how I did that, just follow the same steps, okay, as it is here. So, and wherever I have y equal to 0, I can replace that with y equal to 1. That's how I wrote directly from here, okay. So we know these probabilities as well. This is again the transition probability, that is 1 by 8, and this is 9 by 10. This is nothing but 7 by 8, correct? This probability is 7 by 8. This is 1 by 10. So now 9 by 80, this is again x hat equal to 0, x hat equal to 1. So this notation means whenever it is greater, the decision will be x hat equal to 0. Whenever it is less, whenever LHS is less than RHS, then x hat equal to 1. That is the meaning of that notation, okay? So now the comparison is between 7 by 80 and 9 by 80. You can clearly see that here LHS is greater. That means even if y equal to 1, then the decision will be x hat equal to 0. So you may be wondering why is it happening. So if you see this is because of the fact that this probability, the input being 0, is a very large probability compared to x equal to 1. That is the reason why the optimum receiver, this is the best receiver, you have to see that, okay? The best receiver is doing this. Whatever else you do, in whatever other way you make decision, the performance, the probability of error that we are going to calculate will be higher than the value that we are going to get, okay? So now, what is an error? In this case, whatever be the output, the receiver makes a decision that x hat equal to 0. That means irrespective of the received symbol, it can be 0 or 1. The receiver doesn't care. The receiver will make a decision that x hat equal to 0. This channel is not good for communication, that I agree. But for the sake of solving this problem, this is what is happening here, okay? So the probability of error is this, that I have written here previously. Probability of error is this, correct? Probability of x not equal to x hat, or it is equal to this. So if you see this probability, the receiver is never making this decision x hat equal to 1. So this probability will not come in the probability of error because x hat is never being 1. So x hat is always 0. So probability of error will be this probability. Probability of x equal to 0. Probability of x equal to 0, comma x hat equal to 1. Sorry, x hat equal, what is that probability? X equal to 1, x hat equal to 0. So this is equal to this. So what does this mean? So basically, the receiver is always making a decision that the transmitted symbol is 0, correct? Then whenever the actual transmitted symbol is 0, there is no error. When is an error happening? An error is happening when the transmitted symbol is 1. If the transmitted symbol is 1 and the receiver is making a decision x hat equal to 0, that's an error, right? The receiver is incorrectly mapping the transmitted symbol to 0. That is an error. So an error will happen always when, I can write like this, right? Because this is always 1. Do you agree with that? Sorry, this is always true. X hat is always 0. So this is equal to probability of x equal to 1, which is equal to 1 by 10. So whenever the input is 1, that corresponds to a receiver error, a decision making error. So what is the probability of the input being 1? That is equal to 1 by 10 given in the question. You got it? Any questions? This is a slightly difficult question that I understand, but not that complicated. If you are having some doubts, you can ask now. If not, we will move to the next question. Last probe. Last means you are asking about this probability. Okay. So basically, so if you carefully see, you don't basically look into this equation. Instead of that, you listen to the following argument. Okay. So basically, in this case, when does an error happen? Usually, in a general setting, when does an error happen? An error happens when the actual transmitted symbol is different from the receiver decision, correct? That is an error. In this case, we have seen that the receiver always makes a decision that, correct, the transmitted symbol or x hat equal to 0. This is the decision the receiver makes. Always, this is the decision. So when does an error happen in this case? If the actual transmitted symbol is 0, then there is no error, correct? The decision is also 0. But an error happens when the actual transmitted symbol is 1, correct? Whenever the actual transmitted symbol is 1, the receiver will receive something. It can be either 0 or 1. That I don't know, or that will happen according to the channel condition, right? But whatever be the received symbol, the receiver makes a decision that x hat equal to 0. That means an error happen when x equal to 1. That means an error happen when the input is 1. That means probability of error equal to probability of x equal to 1, which is equal to 1 by 10. Okay. Okay. It seems you agree with that. So, or in other words, you can, how did I write this? Means irrespective of x equal to 1, x hat is always 0. So those are independent. So you can just take product, and probability of x hat equal to 0 is 1. So that will be gone, and which will be equal to probability of x equal to 1. You can visualize in that way also. Okay. Any other question? If not, I will move to the next question. Can I go ahead? Okay. Then let us see the next question. It's two questions together. Okay. This is again related with this receiver and probability of error, but a slightly different form of question, and it's not that difficult compared to the previous one. Okay. So after this, I have two more questions, but I will do one probability related question after this. So yeah, this question is as follows. Bits 1 and 0 are transmitted with equal probability. At the receiver, the PDF, the probability density function of the respective received signals for both bits are as shown below. Okay, you can see two triangles. This is corresponding to this left triangle is corresponding to transmitted bit x equal to 0, and this is corresponding to x equal to 1. What are actually these triangles? These are nothing but the probability density functions. This is nothing but the channel, as I told in the previous case. This is nothing but here, since it's a continuous distribution, instead of p, I will use f. Okay, probability of or f of y given x equal to 0. This is this one, this left triangle, and the right triangle is nothing but the density y given x equal to 1. Since it's a continuous distribution, I am using f. Okay, this is nothing but probability distribution. So now the question, there are two questions. Let us see one by one. The first one is as follows. If the detection threshold is 1, the BER will be, the bit error rate will be. That is the question. So basically we need to find the probability of error. Also it is given a threshold. So this is the threshold. What does the threshold means? It means that, so basically I will denote threshold with say T. Okay. So if the received Y is less than or less than T, then the receiver will make a decision that x hat, the transmitted symbol, is 0 in this case. 0 comes in the left hand side, right? If y is greater than t, x hat equal to 1. Okay. Do you agree with this? So this is the meaning of a threshold. Okay. Agree with that? Okay. So in this case, they have told that t equal to 1. What does that mean? So if you see, this is t equal to 1. So whenever the receiver receives a y that lies in this region, then x hat equal to 0. And whenever the receiver receives something in this region, then x hat equal to 1. So here you can clearly see that if I transmit 0, then what are the ranges of values that it can be received at the receiver side? That lies in between -1 and +1, right? This is +1. It lies between +1 and -1. Agree? Similarly, if the actual transmitted bit is say 1 as given here, then the received value can lie in between 0 and 4. Agree? 0, this is 0 and this is 4. Agree with that? Yeah. Okay. So if you see carefully, okay, this is just like the not like the previous problem, but the decision error will happen. I'm making a statement. If you're okay, you tell you agree with this. Okay. The in this case, if the transmitted bit is 0, then a decision will never happen. Do you agree with that? Do you agree with that? Listen carefully. Yeah, I'll repeat that. If the transmitted bit is 0, that means if it is corresponding to this case, okay, and sticking to the question and threshold is 1, okay, I'm talking in that under that assumption. If the threshold is 1 and if the transmitted symbol is 0, then a bit error or an error will never happen. Do you agree with that? Yeah. What is the reason for that? So whenever I transmit 0, the output can be anywhere between -1 and +1, correct? And whenever the received value is less than or equal to 1 or less than 1, correct, the decision will be x hat equal to 0. That is the meaning of threshold, correct? Whenever y less than, here 1, not sorry, whenever y less than t equal to 1, x hat equal to 0. That means whenever I transmit 0, bit 0, okay, don't confuse with this threshold 1 and bit 1, okay. When I transmit or whenever I am transmitting bit 0, the received value will lie in between -1 and +1. And whenever the received value is less than 1, the decision is in favor of 0, x hat equal to 0. So which means that an error will happen when I transmit bit 1. Not always, but an error will happen in this case. Okay, probability of error equal to, that will happen when input x equal to 1, comma, y less than 1. Do you agree with this? Probability of this. Do you agree with this? That means if I am transmitting 1, let us focus on this scenario. If the transmitted bit is 1, okay, then there is a finite probability for being the received, correct, received symbol being received symbol being less than 1, correct? So which is the threshold is 1. So under this condition, if I transmit bit 1 and the received y value is less than 1, that's an error because the receiver will make a decision that x hat equal to 0, correct? Everyone agree with that? If there is any confusion, please ask. Okay, so this is the only like complicated part in this question. It's not complicated, but this is the idea behind this question. Any questions? If not, I will compute this probability. Okay, then let us compute. So this is nothing but, what is this first of all? That is nothing but this area, right? Is that correct? Not exactly, but that is somehow related with that area, correct? Do you agree with that? So how will I write this? This is nothing but probability of y less than 1 given x equal to 1 into probability of x equal to 1, correct? So this is nothing but f of, this is probability of y given x is nothing but f, right? F of y less than 1 given x equal to 1. So basically that is this second triangle, this triangle, into probability of x equal to 1. Agree with this? This is nothing but the area, this area. Agree with that? That is equal to, or basically you can find it with an integration if you want. That will correspond to that area, integral 0 to 1. So what is the equation of this line? Equation of this line, this is nothing but y equal to x by 4, correct? Because at x equal to 0, y equal to 0, and at x equal to 2, y equal to 4. So that line has an equation y equal to x by 4. So x by 4 into dx, which is equal to x square by 8 between 0 and 1, which is equal to 1 by 8. In other words, that is corresponding to 1 by 8. Yeah, that corresponds to this area. This, what is this value? This height, this is nothing but 1 by 4. You can find out that that is 1 by 4. 1 by 4 into 1 into half bh, right? So that will correspond to 1 by 8. This is 1 by 8, and probability of x equal to 1. Basically, that is missing in the question. Yeah, it is given with equal probability. Okay, you have to see this. Bit 0 and 1 are transmitted with equal probability. What is that equal probability? That is equal to 1 by 2. Correct? So this is equal to 1 by 2 and this is equal to 1 by 8. So the probability of error is 1 by 16. Any questions? Did you understand? Is it clear? Some doubts? Confusions? Can I move to the second part? Okay. Okay. The second part is not uh, it's not to find out any error. Instead of that, this is to find out the optimum threshold to achieve minimum bit error rate. Okay. So to find out the optimum threshold, optimum means it corresponds to optimum receiver. Optimum receiver means, as we have seen, it's the map receiver, right? Probability of x given y. Correct? That means probability of x equal to 0 given y compared with probability of x equal to 1 given y. So this is equal to, I can write it like this, probability of x equal to 0 comma y divided by probability of y compared with probability of x equal to 1, as we have done in the previous case, in the previous question basically. So this is basically comparing the top or the numerator y. This is equal to probability of y. Why is it not working? Yeah. Probability of y given x equal to 0 into probability of x equal to 0 compared with probability of y given x equal to 1 into probability of x equal to 1. So it is given that probability of x equal to 0 and probability of x equal to 1 are equal, 1 by 2. That is given. So this is nothing but comparing. This probability is denoted with f in this case. It's a continuous distribution. Y given x equal to 0 being compared with y given x equal to 1. So basically, we started with the ulta, or in the other way, the conditioning x given y, and we ended up with y given x. This this happened because of this equiprobable inputs, right? So basically, this is known as map rule, as we have told in the previous case, and this is nothing but ML, maximum likelihood rule. Okay. So in some questions, this probabilities won't be given. This input probabilities won't be given. These probabilities. In that case, you can assume that they are equiprobable, and we can use this ML rule. ML rule is just the other way. It is nothing but the channel. This you can visualize as the channel. Okay. So now what is the optimum threshold? That is nothing but whenever this becomes equal, that particular y corresponds to the optimum threshold. Okay. So now, where is the point at which these two density functions intersect? That is nothing but this point, correct? So we need to find that y, this value. That is the optimum threshold. Do you agree? So if you see, before this threshold, f of y given x equal to 0 is greater than f of y given x1, x equal to 1. Similarly, towards the right side of this threshold, this side, f of y given x equal to 1 is greater than f of y given x equal to 0. Agree? So how will we find out that? So first of all, we need to find the equation of this line, and we need to find the equation of this line, and we need to find the intersecting point, correct? So it is very easy. The first line that connects 1, so this is nothing but 0 comma 1 and 1 comma 0, right? This is 0 comma, sorry, this is 0 comma 1 and this is 1 comma 0. It connects those 2 points. The line equation is nothing but y equal to 1 minus x, right? Do you agree with that? Y equal to 1 minus x. And the second one, this we have already found out y equal to x by 4, this equation of the line, equation of this line. So we need to equate 1 minus x and x by 4. 1 minus x equal to x by 4 means x equal to, or 5x by 4 equal to 1 and x equal to 4 by 5. So this is the optimum threshold. So this intersection happens at x equal to 4 by 5. So the answer to the question is 4 by 5. The previous one was 1 by 16. Is it clear to everyone? Any doubts, any questions? If you have some questions, please ask now. Or else we will move to the next question. The next one is not related with communication theory, and that has nothing to do with receiver design or optimal bit error rate or anything. Pure probability question. Okay. So if you have some questions, you can ask now. Can I go ahead? Okay, at least one person. Yes, no. Okay, thanks. Okay, yeah, this is the question. This is a fairly easy question, but again, there is a slight extra bit of work you need to do to get the answer. Okay, to solve the question, you need to have some tool basically. Okay, this is to find the expectation of a random variable. The question is as follows. A fair coin is tossed repeatedly till both head and tail appear at least once. The average number of tosses required is. Okay, understood the question? It's very clear, right? So I have a fair coin, that means probability of head and probability of tail. What does this notation means? It means that when I toss the coin, it's an event. Okay, this H denotes an event. I'm tossing a coin. Then what is the probability of getting a head, or what is the probability of getting a tail? Since it is a fair coin, this is equal to 1 by 2. Okay. So in some questions, you may see the probability of getting a head is slightly different from probability of getting a tail. But in this case, it's a fair coin. And what am I doing? I'm starting to toss the coin. I'm tossing the coin once, twice, thrice, and it goes like that. And when will I stop tossing the coin? I will stop tossing the coin when I get a head and a tail at least once. Okay, so what are the possibilities? Say assume I'm getting a head in the first try and I'm getting a tail in the second try, then I will stop. Okay, or in other words, say I'm getting a tail, I'm getting a head, I will stop. So what is the done this in a previous session? Answer 3. I haven't done this. Did anybody else do this? I don't know. Some in some other sessions. Okay, if not, then I'm not explaining this question. Somebody, okay, but please explain. Okay, but somebody shared this question to me to solve this. That's why I'm doing this. Okay, if you're interested, I can solve. Otherwise, let's stop it here and let us see some other question. If at least one person wants to solve it, I will solve. Okay. Okay, please explain. Okay, then I will do it. Okay, then I will do it. I will do it quickly. I am not wasting time then. Okay, so one thing is very clear. I need to have at least two tosses, right? In order to get, in order to satisfy this condition. So this is one possibility. The next possibility is what? I am getting head and tail, or tail and head. So here in this case, I need n equal to 2 tosses. In this case, I need to get 3 tosses. Is there any other pattern in which I will get or I will meet this condition with n equal to 3? No, right? If I am getting head, and I will stop when I get a tail. If I get a head, I will continue. And whenever I get a T, I will stop. So the sample space of this event will look like this: head, tail, head, head, tail, head, 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 tail. It goes like that. Similarly, tail, head, tail, tail, head, tail, 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 head, and it goes like that. This is the sample space. Agree? So now I will compute some probabilities. First of all, what is the expectation? I am denoting the number of tosses with a random variable, capital N. Okay, N, the random variable denoting the number of tosses. So what is the probability of N equal to, say, 1? This is 0, right? In one toss, anyway, I won't satisfy that. I will not get the result because I need to get at least one head and a tail. Correct? So P of n equal to 1 is 0. Now, what is the probability of n equal to 2? That is nothing but the probability of this plus probability of this. Probability of head comma tail and probability of tail comma head. This is nothing but 1 by 4, 1 by 2 into 1 by 2 plus 1 by 2 into 1 by 2, which is equal to 1 by 4 plus 1 by 4, which is equal to 1 by 2. Similarly, what is the probability of n equal to 3? This is equal to probability of head, tail plus probability of tail, head. This is 1 by 2 into 1 by 2 into 1 by 2, 3 times. That is 1 by 2 cube plus 1 by 2 cube. That is equal to, this is equal to 1 by 4, or in other words, I will write like this. Okay, 2 divided by, not 2 divided by, I will write it as 2 square. Okay, so now probability of n equal to 4. Similarly, you will get 1 by 2 power 4 plus 1 by 2 power 4. Agree? If you have some doubts, you ask. Okay, 1 by 2 cube. So in general, some integer which is greater than 1, probability of n equal to n will be 2 power n minus 1. Is it clear? I hope it is clear because you have seen this question before. So expectation of n is nothing but, this is the formula for expectation. In this case, n varies from 2 to infinity, right? N into probability of n equal to n. So this is equal to summation n equal to 2 to infinity n into 1 minus, sorry, n into 1 by 2 power n minus 1. So probability of n equal to n, I'm just plugging in this value here. Okay. So now this is the, like, up to this, everything is very straightforward. And now we need to compute this value, this summation. So in order to do that, I will quickly do this. Let us substitute n equal to 2 first. Then we will get 1 by 2 power 2 minus 1 is 2 power 1. So 1 by 2 plus 1 by 2, 2 times, right? Or maybe I will write like this, 2 into 1 by 2 plus 3 into 1 by 2 square plus 4 into 1 by 2 cube, etc. So this I will write it as 1 by 2 plus, again one more 1 by 2 plus 1 by 2 square, 1 by 2 square 3 times. So I'm writing the next term 4 times, 1 by 2 cube. I am making it into different layers or different rows. Okay, it goes like that. The next term will come 5 times, the next one 6 times, and it goes like that. So basically it grows diagonally as well. Correct? Now, what is the speciality of these rows? Basically, there is a summation here as well. Okay, so what is the sum of this row geometric progression, right? Infinite geometric progression or geometric series in this case. And R is the common difference. Sorry, common ratio. Common ratio is 1 by 2 because 1 by 2 into 1 by 2 is 1 by 2 square. 1 by 2 square into 1 by 2 is 1 by 2 cube, etc. And the first term A is again 1 by 2. So this is equal to 1 by 2 divided by 1 minus 1 by 2 is again 1 by 2. So this is equal to 1. So the next row is also the same term. So the sum is again 1. So in this case, the third row, you can see it is again a geometric progression, but the first term is 1 by 2 square, but the common ratio is 1 by 2 again. 1 by 2 square into 1 by 2 is 1 by 2 cube. The next term will be 1 by 2 power 4. That is nothing but 1 by 2 cube into 1 by 2. Correct? So this will be, the first term is 1 by 2 square divided by 1 minus 1 by 2. So which is equal to 1 by 2. So if you see the next term, the next row will have a sum 1 by 2 cube divided by 1 minus 1 by 2 corresponding to this row. Okay, the sum. So which is equal to 1 by 4. So here you can see another geometric progression is being formed. Correct? So, and excluding, there is a 1 here that we will consider later. Here I have a geometric series 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus etc. goes like that. This has a sum, the first term 1 divided by 1 minus common ratio 1 by 2, which is equal to 2. Correct? And we have excluded this 1. So the total sum is 1 plus 2, which is equal to 3. So as somebody pointed out, even before reading the question, so the answer is 3. Great. Any questions? Any questions? Okay. If not, it's 6:59 in my computer. It's 6:58. Okay, 6:58 in my this device. So I don't have time to solve one more question. I will show the question, but this is the question that I wanted to do. Maybe I will do this in the next class. Okay. So next class, I will do again some questions related with communication. If you have some suggestions, you can send me. And afterwards, I will do some, like not in the next class, maybe in the class that are coming after the next week. I will do some questions related with probability theory and linear algebra matrices. Okay, basically engineering maths related questions. I think we will get hopefully 4 more weeks before the gate exam, if I am correct. Okay, if you have some questions, you can ask now, or if you have some suggestions for questions to be done in the coming weeks, you can like tell me now, or you can share later. Okay. Any questions? So far, so good. Okay. If there are no questions, we will see again last week. Okay, how to revise in the last week of gate exam. So basically, even though I'm not doing any questions related with field, electromagnetic field theory and all, I think for such topics you will have to memorize some of the formulae, right? I don't recollect the topics exactly, but I guess there are some formulae to be like to be remembered while going for the exam. Some something related with skin depth, something related with antenna theory, some questions, right? For all other questions, you have now it's more about revising the concept for some other topics like communication theory and all. So, and also some pattern, some questions will be repeated again and again and again in all the exams. Some patterns, not the question as such, but by making some slight changes, they will ask a lot of questions, especially in DSP, this DFT related questions, discrete Fourier transform related questions. So you can see the previous year questions and you can like again be comfortable with those questions. Um, then about maths, I don't have any like, suggestion as such because for maths, except for this probability theory, I think for probability theory, some questions are like just like this question that we have seen. These kind of questions are repeated many times, not exactly like this to compute an expectation of a random variable that has infinite probability, some coin tosses experiment or some questions that we have discussed previously like this. What is that? Not this one. Okay, somewhere I have discussed. Okay, yeah, the questions like this. These kind of questions have repeated multiple times. So these kind of questions you can get familiarized with again. And yeah, that's about probability. Then coming to matrix theory, some questions are related with this eigenvalues and all are repeated many times. Not the exact question. What I mean is that those areas. So you can focus more on such problems. Okay. And yeah, so that's all that I can tell. And for other topics like uh, some circuit related area, I'm not very sure about that. Okay, so if you like want to ask, you may ask to somebody else who are handling the classes. So that's about this communication and signal processing and all. Okay, I hope I told whatever I'm remembering and I answered to best of my knowledge. Okay, so any other thing, any other questions, any other doubts? Okay, then let us wind up for the day. Thank you. Let us meet in on the coming Tuesday. Thank you.